welcome to the first video, or first proper video of the series, so Unit 1, Electrical Circuits. Like it says here, this is for both those of you doing separate science and those of you doing the double award science. Okay, so objectives then. What are we going to cover in this presentation? We're going to cover the key circuit symbols. We're going to try and understand what current, voltage, resistance and powers are. We're then going to use various laws such as Ohm's laws, resistors laws and power to calculate unknown quantities in circuits. And then the final thing is we're going to hopefully learn the IB characteristics or current voltage characteristics of the... Okay, here a whole list of useful links. Okay, circuit symbols then. So on screen are the key circuit symbols that you need to learn. The top ones that are in the 2 bank, so here, this section, everyone needs to learn them, whether you're doing separate science or double award, and this section down here tends to only come up more on the double award. Sorry, not on the double award, on the separate science. These power supply symbols are just a fancy way of drawing a cell or a battery. Generally both will be acceptable, so don't worry about it too much. Okay then, so our key terms. So let's start off here, some key terms that you need to learn. So we've got series, parallel, current, voltage, power, resistance. Alright, you can pause the video now if you want to have a go at writing your own definitions. If you don't want to do that, here are the key ones then. So, series. This is where we have components that follow on from each other. We only have, the important bit is one path. So if you trace around a circuit with your finger, you can only go around it once. Parallel, we have different paths. So to get back to where we start, we've got to go round more than once to get back to go through everything. Parallel circuit, current. Now current, sometimes it's difficult to see, but current has the symbol of an I. This comes from the old times when they viewed current as intensity, so that's where it comes from, and that's our flow of charge. So any flow of charge around a circuit is a current. It is measured in amps, which is a capital A, and we use an ammeter to do that. Voltage, which has the letter V when we use it in symbols, is our energy per unit charge. So the way I always like to think about this is current is basically how quickly our electricity flows around a circuit. Quick, yeah, it's a poor model. That's why it's better not to think about it this way. Whereas voltage is sort of how much push it has as it gets around there. Measure voltage in volts, and we use it using a voltmeter. You might see in some books correctly, more correctly than voltage, more correctly they call this potential difference, or PD. WJEC allows you to use either voltage or potential difference, so that's just there for completeness. Power has the symbol P, and that is the rate of energy transfer. Now wherever we see rate of, that means per unit time, means something divided by time. So it's energy transfer divided by time, and that's measured in watts, or a capital W. And then our final one is resistance. Resistance, we give the letter R in equations, and this is our opposition to a flow of current. So anything with resistance is going to try and stop a current from flowing through it. It's measured in ohms, and ohms is this symbol here, that's the Greek letter omega. And resistance is caused then basically the structure of a material. So if you think about a metal, metals contain positive ions, and as electrons come past them, these are going to get attracted towards each other, but they're also just in the way. You're going to get the electrons smacking into them, and it's going to cause an opposition to this flow. Okay, key circuit laws. So the first wordy ones that are going to come up you need to learn, and then the equation ones you don't need to learn, but you do need to be able to put them in the triangles that are shown on the screen. So, series circuit. Current is the same everywhere. because if you've got two things in series, the current coming into one has got to get out of it and it goes straight into the next one. So there's nowhere for the current else to go, so it's got to be the same. They share voltage, so whatever voltage is supplied to the components, they share it. Not shared equally, doesn't have to be shared equally, unless they have the same resistance, then it will be. But adding more things in series is always going to increase the overall resistance of a circuit. Because if you think about it, the current's got to go through each one, so it's going to get harder and harder and harder for that current to get through. For parallel circuits, components in parallel have the same voltage. Because the electricity will only go through one or the other, it needs to give all that voltage away before it gets back to the cell, so same voltage. But because that electricity has now more than one way to go, the current is going to split. Alright, so we have different currents in our branches. Think about it as well, we've got more branches, more paths for the electricity to go through, for the current to go through, therefore our resistance decreases because we can actually have more current flowing. So adding things in parallel is always going to decrease the resistance. Okay, on to the mathsy side then. So Ohm's law is going to be voltage times current, doesn't matter which, sorry. Ohm's law is voltage is going to be current times resistance, can't read. Yeah, so we have voltage, current, resistance, voltage, current, resistance. So we put voltage in the top of the triangle and then these two go in the bottom of the triangle. Now power, well, power is the rate of energy transfer. So it's going to be energy divided by time, or energy is power times time is another way of writing that. But if we've also got the power is current times voltage, more often known as P equals IV, as written in this triangle. Well, what we can do is we can take Ohm's law, our voltage bit, and substitute in, and what we get now is current squared times resistance. You could in theory put current in there, and that time what you would get is voltage squared divided by resistance. That's not technically on our spec, but I have seen cases where it makes life a lot easier if you use that equation, and it means you avoid doing multiple steps. Okay, so IV characteristics. Alright, so there's three graphs you need to learn, three components. Filament light bulb. So for a filament light bulb, it is this curved shape. So as voltage increases, current increases. However, once we get to large voltages, the increase in current slows down. Why is this? Because as we increase the current flowing through a bulb, it's going to get hot. If you think about a filament light bulb, one with a little wire in it, they get hot. Hot objects have a higher resistance than cold objects. Objects with a higher resistance for the same voltage will have a lower current flowing through them. So that's why it's that shape. If we have a resistor or a wire at constant temperature, then here voltage and current are directly proportional. This means that as one is doubled, so is the other. They will follow Ohm's law. Any component with a graph that looks like this, we call an ohmic conductor, and they follow Ohm's law. And the gradient of this line, how steep it is, the gradient here will be 1 divided by the resistance, which is quite useful to know for that. And a diode. So diodes are very special components, and as voltage is increased in the positive direction, then the current quickly increases because they've got very little resistance. However, if we put a negative voltage across them, no current flows. They are designed to only allow current to flow in one direction. So that's our diode graph. Okay, so resistors, combining resistors. Well, we already said in series, adding resistors adds the resistance. So the total resistance in any circuit is the sum, or you just keep adding all the resistors. Now the ones, these little, or the twos, these subscripts, just are the numbering of our resistors. We could number them in any way. You know, it could be 1, that could be 2, that could be 3, that could be 4. It doesn't matter which way we number them, but that's how we go with that. Okay, what about parallel then? We already said adding resistors in parallel decreases our overall resistance. And the formula that goes with this actually is a little bit tricky. So here where we have them in parallel, like here's our parallel, what we actually get is 1 over the resistance equals 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. What a lot of students do when they do this calculation is they forget that this gives us 1 divided by the total resistance. So to get from there back to the total resistance, you've got to do whatever you've got to the power of -1. So somewhere on your calculator there will be just that button there. Press that one once you've got your answer, and that will give you your proper answer. That will give you what the resistance is. Okay, final getting on to the final pieces of this. So reactive components. Reactive components react to their surroundings, generally changing their resistance depending on the environment. We've got 2 you need to know about. An LDR, light dependent resistor. These work with a little crystal in them that basically when light falls on them begin to conduct electricity. So they have high resistance when they're dark and low resistance when they're light. Very useful in things like security lights. So if you've got lights in your back garden that only come on at night, they will have in them an LDR, something that is sensitive to light, so that when you can set it so that they only come on when it's dark enough. And the other one we need to know about are thermistors. Now these have high resistance when they're cold and low resistance when they're hot. So we can use them in temperature sensitive circuits. So for example, something like a kettle might have a thermistor in it. We can use them as digital thermometers quite easily, and that's generally where they're used. Now they're not linear, you don't get a straight line on both of them, they're both a curve like so. So this graph would be very similar for LDRs and for thermistors. Obviously this is for a thermistor because it says temperature. If it was for an LDR, then this bottom axis would be light. Okay, on to probably what is the hardest part of solving resistor, of using electricity, is solving circuits, trying to find out unknowns. So this circuit here has enough information in it that you actually can measure, or you can calculate what every reading on these voltmeters and ammeters will be. And there's a series of steps to follow. So, step 1. I would always go about highlighting which resistors are in parallel and which resistors are in series. So let's have a look at which are in parallel. So our parallel ones, we've got, pardon me, that one there, they're in parallel. And we've got another set in parallel. Okay, so we then want to calculate the equivalent resistance of these resistors. What I'll do is, got a bit more space on the next slide, go through this in a bit more detail on the next slide. Then we work out what's in series with each other. So once we've worked out these and we've worked out these, what we should notice is that we've then got 2 in series with each other. We then know what the total resistance for this circuit is, and we can use Ohm's law to calculate the total current. So once we know what the resistance of all of this lot is, we can work out what current is going through this ammeter here. And then it's just a case of using Ohm's law and your answers that you've got to the first few bits to work out the rest of what's on this. Okay, so let's follow these steps. Let's actually do this then. So, step 1, we're going to highlight our resistors. So like we did before, we've got those 2. And we've got those 2. Step 2, calculate our resistance. So what I'll do is I'll do the blue ones in blue. So we have 1 over R here. So 1 over the blue resistance is going to be 1 over 100 plus 1 over 200. which is not 1 over 300. Remember, we need to make sure the bottoms are the same, although you've got a calculator to do this, so it doesn't actually matter. Let's do it on the calculator. 1 over 100 plus 1 over 200 is 3 over 200. So that's not our actual resistance. Our actual resistance, remember, is going to be 1 over this value, so we press x to minus 1 and equals, and that gives us 66.7 ohms. Now, those of you who probably can see the calculator or have done it will say, hang on a minute, that's got a 6. Why have you written 7? Well, it's 6 reoccurring. It's 6. You might be able to see with a little dot on the top. You might not be able to see it because of the light. That little dot means reoccurring, so that means that that goes 66666 on forever. So if we're rounding to 3 significant figures in this case, that final digit has to round up to 7. Okay, let's do the same for the green. So the green is going to be 1 over 50 plus 1 over 100, which in this case is going to be 3 over 100. So the green R is going to be 33.3 ohms. We'll just check that, but so 1 divided by 50 plus 1 divided by 100, nope, to the minus 1, yeah, 33.3. Don't round up in this case because although it's 3 reoccurring, 3 is less than 5, so we don't round up. Okay, next job, we identify that what we've just done we will have in series. So in series, we'll go over to this side. R now is going to equal 100 ohms. Why is it 100? Well, it's 66.7 plus 33.3 comes to 100. Now the next step was to work out the current. So I is V divided by R. So that's going to be 10 divided by 100, which is 0.1 amps. So this answer here, 0.1 amps. Okay, so the next easiest bit to work out are the two voltages here and here. Now remember we said voltage will split by the resistance. So we just use Ohm's law in each case. We do V equals I times R. So for this first one, it's going to be our 0.1 times by what the resistance of these two together is. So that's 66.7. 66.7. So this one is going to be 6.7 volts. And this one is going to be 3.3 volts. I know this one here is going to be 3.3 volts because this plus this must equal 10. Whatever voltage we start off with is going to be used up by the time we get back. So 6.7 plus 3.3 equals 10. Then the final bit is to work out what these two ammeters are. So we know we've got a voltage of 6.6. We know we've got a voltage of 6.6. A voltage of 6.6. We know we have a resistance of 200. So here we're going to do our 6.7 divided by 200 to give us 0.0335 for this ammeter. And then likewise here, we're going to have 3.3 divided by 50. And that's going to give us a current of 0.066. Let's put the decimal point better in there. Now, one thing to take care with, we know we've only got 0.1 amps coming in, so none of these values here can actually be higher than that 0.1 amps. If you do get a value higher than what you've said is coming in, either this bit is wrong or somewhere down here is wrong, so that's something to take. Okay, so over to you. Like I said, if you watched the introduction video, it if you're watching this on YouTube, the link to this will be in the description. If you are watching this on the PowerPoint, if you stop the PowerPoint show and just click on this picture here, it should load up the Acrobat file, the PDF that has a bunch of questions for you to do. On the next slide will be me going through these questions, discussing the answers. Okay, so welcome to this video going over the questions, hopefully, that you've opened on the previous slide and you've had a go at. You could, I suppose, do them going along at the same time as me, but it's definitely worthwhile having a go at those questions before watching this video. Okay, so in this first question, we're asked to calculate different voltages and currents throughout the circuit. This is very similar to following the methodology that I put in the previous slides. So we're asked to calculate the voltage across R1. So let's look at R1. Let's see what we already know. Well, we know it's a resistor, so we know that the actual resistance of R1 is 2 ohms. That is written on the page. And if we go a little bit further back round, we can see that there is 2 amps going through through R1, because it's in series with that ammeter. So we know that the current is 2 amps. We want to know the voltage, and the voltage is going to be using Ohm's law, which is going to be 2 times 2, which is 4 volts. Okay, use your answer to part 2 to calculate the current through each of the parallel resistors. Okay, so we follow a similar idea. So we know that R2 is 12 ohms. We know that V2, well, V2 here, if we've used up 4 volts on R1, that leaves us 8 of the 12 left. So it's going to be 8 volts. And then we get our current this time is going to be 8 divided by 12, which is 0.67 amps. Now, on your calculators, if you've done that on a calculator, what you'll get is 0.6 and a little dot. That little dot remembers reoccurring, so that's 0.6, and the 6 go on forever. So we need to round up because it's higher than 5, so we round up here. And if we're doing 3, well, the current through number 3, following the same idea, this time is going to still be 8 volts because 2 and 3 are in parallel, they have the same voltage, divided by this time the resistance of 3, which is 6, to give us 1.33 amps. Now, eagle-eyed amongst you will notice something about those 2 values, that they add up to the 2 amps that we started with, which is good because whatever current goes into that split must come back out of it. Okay, the next question then. A 12 and a 16 ohm resistor connected as shown. Use the equations from page 2 to calculate the total resistance of the circuit. So this time we're looking at combining resistors. So we've got the 12 and the 6 are in parallel. So we first do 1 over 12 plus 1 over 6, which will give us 3 over 12. Now remember, that's not the value for R, that's 1 over R. So 1 over R is 3 over 12. So therefore R is going to be 12 divided by 3, which will be 4 ohms. But that's not the final answer, because that 4 ohm resistor is then in series with the 16 ohm resistor. So we do 4 plus 16, which gives us 20 ohms, and that's our final answer. A brand new battery is used in the circuit. The manufacturer states the new battery can transfer a maximum of 75.6 kilojoules of energy. The current from the battery is measured as 15 amps. Use this equation and another one to calculate the time in minutes that it will last. Okay, so first things first, we need to work out what the power of this circuit will be. So we do power is 1.5 squared times by the 20 we had in our previous question. So this is our overall power. So 1.5 squared times by 20. is 45 watts. So what that means is that every second this battery transfers 45 joules of energy. So we now need to work out how many seconds, or how many seconds 75.6 kilojoules of energy will need, or how much power we will need. Sorry, let's try that again. We now need to calculate the time required to transfer that amount of energy at that power. So we have the time is going to be energy no, let's rewrite that again. So energy is power times time. So time, is going to be energy over power. Okay, so we know we've got a power of 45 watts, and we know that we've got a current. We know the power now is 45 watts. So we've now got that energy is power over time. So time, that's not right, is it? Sorry, let's get that right. We know that energy is power times time. So we have time is going to be energy over power. So our energy is 75,600 divided by our power, 45. Why 75,600? Because it's 75.6 kilojoules, so 75,600 joules. So we do that sum, 75600 divided by 45 gives us 1680. But that's in seconds. We need it in minutes. So we divide that by 60 to put it in minutes, which is exactly 28 minutes. Okay, so this question. Diagram shows a lamp connected to a battery and a variable resistor. Describe how the circuit can be used to obtain a series of measurements to show how the current through the lamp varies with the voltage across it. You should include the names of the measuring instruments needed, add these measurements to the circuit diagram above, describe how a series of measurements is obtained. Okay, so we need to add in some measuring things. We will need to add in an ammeter and a voltmeter. Ammeter, that goes in series with the circuit, so we can just draw that wherever, somewhere on it. And our voltmeter needs to go in parallel with our bulb. So to get a series of measurements, what we are going to do is, step one, we're going to use the variable resistor to change the voltage across the bulb from 1 to, now we're not told any other measurements, so we're going to say 12 volts in 1 volt increments, or 1 volt steps will do, 1 volt steps. Step 2, for each voltage measure the current. In fact, let's write it properly, current. Step 3, describe how the circuit can be obtained. Yeah, and that, to be honest, that's all we need to do for this. We could say about drawing a graph, but it's not asking us to process the results. So that's all we're going to do. Okay, for this question then, the current to the lamp was measured up to 12 volts. The result of the graph is shown on the grid below. Use the grid to find the current when 6 volts is applied. So you're going to go up from 6 and across, and that gives you a reading of 2 amps. Okay, so we then use the equation resistance is voltage divided by current to calculate the resistance. Well, we've just said that the current was 2 amps, the voltage is 6, so the resistance is going to be 6 divided by 2, which is 3 ohms. Use an equation for page 2 to calculate the power. A couple of ways you can do this. We want power, we might as well do I times V. So that's going to be 2 times 6, which is 12 watts. Lamp is replaced by a resistor, which remains at a constant temperature of 10 volt. Constant temperature. At 10 volts, the resistor and the lamp have the same resistance. Add a line to the graph to show how the current through the resistor varies with this voltage. Okay, so our line is going to start at 0, 0, and it's going to go up to here to be the same point as 10 volts as our bulb. So straight line from here up to here. Okay, thanks for watching this video. Well done for making it through right the way to the end as well. If you liked it, click like. If you got any comments about stuff that's missing, any improvements, anything you didn't understand, leave them in the comments below. If you look around me, there should now be the playlist for all of these videos, along with YouTube's algorithm recommended one of our other videos that you should go and watch. Also, don't forget to subscribe to the channel, follow us on Twitter, link in the description, just to see the other sort of stuff that we produce.